Consider the following example of a skater on a ramp. The height of the ramp is 4 meters and the ramp makes an angle of 27 degrees to the horizontal ground. The mass of the skater and his skateboard is 70 kilograms. If we raise the skater and his skateboard to the top of the ramp, we are giving them gravitational potential energy. How much gravitational potential energy has been gained by them? The potential energy gained is equal to mgh, where m is 70 kilograms, g is 9.8 kilograms meters per second squared, and h is 4 meters. This comes to 2,744 joules. This is the total energy of the skater and his board. Now let's assume the ramp is frictionless. The skater will start to roll down the ramp due to gravity. As he rolls down, he is converting his potential energy into kinetic energy and increasing in speed. This can be seen in the energy graph and the speed dial. The amount of potential energy at any point in time is dependent on the height of the skater at that time. The rest is kinetic energy. Halfway along the ramp, at an elevation of 2 meters, the skater will only have half of his initial potential energy. So at this point, half of the mechanical energy is potential and half is kinetic. When the skater gets to the bottom of the ramp, all of the potential energy has now been converted to kinetic energy. And of course, kinetic energy is equal to half mv squared. So what is the speed of the skater at the bottom of the ramp? So one can see that the higher the starting point on the ramp, the more potential energy the skater will have, which can be converted to kinetic energy, so the faster the skater will be at the bottom of the ramp. Now let's add friction. The skater starts at the same elevation of 4 meters with a potential energy of 2,744 joules. As the skater begins to roll down the ramp, the rolling resistance between the ramp and the skateboard wheels, as well as the resistance in the wheel's bearings, produces a frictional force of 150 newtons. Recall that work done by a force is equal to the force times the displacement times the cosine of the angle between the force and the displacement. Since friction always tries to oppose motion, then the frictional force vector points up the ramp while the displacement vector points down the ramp. So the angle between them is 180 degrees. And of course, the cosine of 180 degrees is -1. So the work done by friction takes energy away from the skater. So what is the total length that friction does work? That is, what is the displacement, x, in the work formula? The length of the ramp can be determined by simple trigonometry to give us 9 meters. What then is the total work done by friction? Using the work formula, this gives us the work done by friction to be 1,350 newtons. Since friction takes away energy, then the skater and his board in the system loses this energy. So by the time he gets down to the bottom, his final energy will be his initial energy minus the work done by friction, which is 2,744 joules for the potential energy minus 1,350 joules for the work done by friction. This gives us 1,394 joules. And of course, his energy at the bottom of the ramp is all kinetic. So what is his speed at the bottom of the ramp when there's friction? As we would expect, his speed at the bottom is slower when there's friction compared to when there is no friction.